Hello there, and welcome to the Sleepy Astronaut, where curiosity gets cozy and the cosmos whispers its secrets as you drift towards slumber. Tonight's gentle voyage takes us on an extraordinary journey to explore one of the most intriguing visitors our solar system has ever received, a mysterious interstellar traveler that might just be carrying the seeds of life itself to Mars. But before we embark on this cosmic adventure, I'd love to know where in the world you're listening from tonight and what time zone you call home. Fitting, isn't it? A story about life traveling across the vast distances of space. And here we are, scattered across our own little planet, each arriving at this moment from our own unique corner of Earth. If you find this celestial tale soothing, thought-provoking, or simply a peaceful way to wind down after a long day, I'd be ever so grateful if you gave the video a like and perhaps subscribed. It helps this little sanctuary of science reach other stargazers who might need a moment of cosmic calm. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll drift off, knowing something remarkable about the possibility of life spreading between worlds. So settle in, take a slow breath, and let's begin our exploration of what might be the most extraordinary delivery in the history of our solar system. On a quiet summer morning in Chile's Atacama Desert, something remarkable happened that would forever change our understanding of what visits our cosmic neighborhood. It was July 1st, 2025, when the automated telescopes of the Atlas survey system detected a faint smudge of light moving against the starry backdrop. What they had discovered wasn't just another comet. It was something far more extraordinary, an interstellar visitor traveling faster than anything bound by our sun's gravity, a cosmic wanderer that had journeyed through the cold darkness of space for potentially millions or even billions of years, carrying with it secrets from another star system. This celestial traveler received the designation 3I ATLAS, where the 3I indicates it's only the third confirmed interstellar object ever detected passing through our solar system following the mysterious cigar-shaped Oumuamua in 2017 and the more comet-like Borisov in 2019. But 3I Atlas is different in ways that make it particularly intriguing for those who study the possibility of life spreading between worlds. Imagine, if you will, a cosmic snowball roughly 3 miles across, hurtling through space at an almost incomprehensible speed of 58 kilometers per second, relative to our sun that's fast enough to travel from New York to Los Angeles in about 2.5 minutes. This isn't just any ordinary chunk of ice and rock, though 3I Atlas weighs an estimated 33 billion tons, making it by far the most massive interstellar object we've ever had the opportunity to study. Its sheer size alone sets it apart from its interstellar predecessors. But size isn't the only thing that makes this visitor special. It's what the comet is made of that has captured the imagination of scientists around the world. When the James Webb Space Telescope turned its incredible instruments toward 3I ATLAS, the data revealed something unexpected and wonderful. The comet is unusually rich in carbon dioxide, with smaller amounts of water, ice carbon monoxide, and other organic compounds. Essentially, it's a frozen repository of the basic chemical building blocks that life as we know it requires. This composition tells a story of formation in the outer reaches of another star system, where temperatures were so cold that these volatile substances could freeze solid and remain preserved for eons. The carbon dioxide-rich nature of 3I Atlas is particularly fascinating because it suggests the comet formed in conditions similar to those found in the outer regions of our own solar system, where life might have the best chance of surviving a journey between stars. But here's where our story takes an almost poetic turn. As 3I Atlas races through our solar system on its hyperbolic trajectory, it's not just passing by at random. Its path through space brings it remarkably close to Mars, closer than any interstellar object has ever approached another planet in our solar system on October 3rd, 2025, just weeks before the comet reaches its closest point to the Sun. 3I Atlas will pass within 18 million miles of the red planet. Now, 18 million miles might sound like a vast distance, and in human terms it certainly is, but in cosmic terms this is practically a close encounter. The gravitational dance between the comet and Mars, during this approach, creates conditions that have never before been observed or studied in real time. This timing couldn't be more perfect for those who study one of science's most intriguing possibilities, the idea that life might spread between worlds on the backs of comets, asteroids, and other cosmic travelers. This concept, known as panspermia, has ancient roots, stretching back to Greek philosophers, who wondered whether the seeds of life might be scattered throughout the cosmos, like dandelion seeds on a cosmic wind. The modern scientific understanding of panspermia suggests that hardy microorganisms might survive the harsh conditions of space, protected within rocks or ice, eventually finding their way to new worlds where they could take root and flourish. The word panspermia itself comes from ancient Greek meaning all seed, and it captures something beautiful about the possibility that life might be a cosmic phenomenon rather than a rare accident that happened only on Earth. The theory suggests that rather than originating independently on each world, life might travel between planets and even between star systems carried by natural spacecraft like comets and asteroids. This would mean that life as we experience it here on Earth might have cousins scattered throughout the galaxy, all sharing a common ancestry that traces back to some primordial world we may never identify. When we consider 3I Atlas through the lens of panspermia theory, several remarkable coincidences begin to emerge first. There's the comet's composition, rich in carbon dioxide and organic compounds, that could theoretically support microbial life during a long journey through space. Then there's its substantial size, providing ample protection from the deadly radiation that pervades interstellar space. And finally, there's its trajectory, bringing it closer to Mars than any interstellar object has ever approached another planet in our solar system. These factors combine to create what might be described as ideal conditions for a theoretical life-seeding event. But before we get carried away with speculation, it's worth understanding what we know about life's ability to survive in the harsh environment of space, and the answer might surprise you. Experiments conducted on the International Space Station have shown that certain hardy microorganisms, particularly a remarkable bacterium called Deinococcus radiodurans, can survive exposure to the vacuum of space. Cosmic radiation, extreme temperature fluctuations, and other hostile conditions for years at a time. This bacterium earned the nickname Conan the Bacterium, for it's almost supernatural to withstand conditions that would instantly kill most other life forms. These space station experiments revealed something fascinating about survival in the cosmos. When bacteria were arranged in clumps or masses, the outer layers would die from radiation exposure, but they would form a protective shield that preserved the organisms deeper within the cluster. As long as the cluster was thick enough, the bacteria at the core could survive for extended periods, even in the harsh environment of space. This discovery provides a potential mechanism by which life could survive not just short trips between planets within a solar system, but potentially even the million or billion-year journeys required for interstellar travel. The protective principle demonstrated by these experiments scales up beautifully to objects the size of 3. Atlas scientists have calculated that rocks at least 1 meter in diameter are required to effectively shield microorganisms from galactic cosmic radiation during space travel. 3I Atlas, with its diameter of potentially over 3 miles, provides thousands of times more protection than the minimum required. This means that if any microorganisms were embedded within the comet's nucleus when it began its interstellar journey, they would have been exceptionally well protected during their cosmic voyage. Recent discoveries on Mars add another layer of intrigue to our story. NASA's Perseverance rover has been finding increasingly compelling evidence that the red planet once harbored conditions suitable for life, and may have preserved signs of ancient microbial activity in its rocks. The rover's analysis of samples from Jezero crater revealed the presence of organic carbon compounds, iron-rich minerals, and chemical signatures that on Earth would be associated with biological processes. While these findings don't prove that life existed on Mars, they demonstrate that the planet has the chemical and geological conditions necessary to preserve evidence of life, whether that life originated on Mars or arrived from elsewhere. What makes the timing of 3I Atlas's visit so remarkable is that it coincides with this golden age of Mars exploration. We have more eyes on the red planet now than ever before, with multiple rovers, orbiters, and landers all equipped with sophisticated instruments capable of detecting changes in the Martian atmosphere or surface. This means that if 3I Atlas does deliver any material to Mars, whether biological or simply organic, we have the best chance in human history of actually observing and studying such an event in real time. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter will be specifically watching for 3I Atlas during its closest approach to Mars, providing unprecedented observational coverage of what might be a panspermia event in action. Meanwhile, on the surface, Perseverance and other rovers will be monitoring the Martian atmosphere for any unusual changes or new compounds that might arrive, courtesy of our interstellar visitor. This coordinated observation campaign represents the most comprehensive study of a potential life-seeding event ever attempted. But how exactly could material from 3I actually reach Mars? The physics involved are both fascinating and complex. As the comet approaches, the sun's solar heating causes its icy surface to sublimate, turning directly from ice to gas. This process creates the spectacular tail that makes comets so beautiful to observe. But it also ejects countless particles of dust, ice, and organic material into space, while most of this material would normally be swept away by solar wind. The comet's close approach to Mars creates unique gravitational and dynamical conditions that could theoretically allow some particles to be captured by the red planet's gravitational field, or to intersect with Mars' orbital path. The mechanics of this potential material transfer involve processes that operate on scales both vast and minute. When 3I Atlas reaches its period of maximum activity near the Sun, it will be releasing enormous quantities of gas and particles at velocities that, while insufficient for direct ballistic transfer to Mars, could still contribute to a more subtle form of cosmic seeding. The solar wind, that constant stream of charged particles flowing outward from our star, acts like an invisible river carrying cometary material throughout the inner solar system. Particles ejected from 3I Atlas could be swept up in this solar breeze and distributed across millions of kilometers of space, creating diffuse clouds of organic material that Mars might encounter during its own orbital journey. This isn't unlike how dandelion seeds drift on terrestrial winds, settling in places far from their parent plant. The comparison isn't merely poetic. The physics of particle dispersion in space follows similar principles to wind dispersal on Earth, just on an incomparably grander scale. Mars, with its thin atmosphere and relatively weak magnetic field, presents fewer barriers to incoming microscopic particles than Earth would. Where our planet's thick atmosphere and strong magnetic field deflect or incinerate most incoming debris, Mars offers a more welcoming environment for the gentle settling of cosmic dust and organic particles. The question of whether microorganisms could survive not just the interstellar journey, but also the final approach and delivery to Mars, brings us to some remarkable recent discoveries about life's tenacity. Studies conducted in Mars analog environments here on Earth have shown that certain extremophile bacteria can survive in Martian soil conditions for extraordinary periods. When researchers subjected the hardy Deinococcus radiodurans to simulated Martian conditions, including the planet's characteristic cold, dry environment and elevated radiation levels, they found that buried specimens could potentially remain viable for hundreds of millions of years. These findings transform our understanding of what constitutes a habitable environment. Rather than requiring the lush, temperate conditions we associate with life on Earth, these studies suggest that life could persist in the Martian subsurface for geological timescales. If 3I Atlas were to deliver even dormant microorganisms to Mars, they wouldn't need to immediately find perfect conditions for growth. They could essentially hibernate in the Martian regolith, waiting for more favorable conditions that might arise through seasonal changes, volcanic activity, or other planetary processes. The concept of dormancy in extreme environments isn't science fiction. It's a well-documented survival strategy employed by life on Earth. Bacterial spores, for instance, can remain viable for thousands of years in frozen or desiccated conditions, springing back to life when moisture and nutrients become available. Some researchers have even claimed to revive bacteria from salt crystals hundreds of millions of years old, though these claims remain controversial. What's not controversial is that life has repeatedly demonstrated an almost magical ability to persist in conditions that would seem utterly hostile to biological processes. This resilience becomes even more remarkable when we consider the journey that any hypothetical passengers aboard 3I-ATLAS would have endured. Traveling through interstellar space for potentially billions of years, exposed to cosmic radiation, extreme cold, and the vacuum of space, yet protected within the comet's icy nucleus like seeds within a cosmic fruit. The very idea challenges our Earth-centric assumptions about what life requires to survive and thrive. Recent advances in astrobiology have revealed that Earth's most extreme environments often serve as analogues for conditions elsewhere in the solar system. From the sulphurous hot springs of Yellowstone to the radiation-soaked depths of nuclear reactors, from the crushing pressures of deep ocean trenches to the acid-drenched waters of volcanic lakes, life has found ways to not just survive, but flourish in conditions that would quickly kill most organisms. These discoveries have expanded our concept of habitability far beyond the narrow zone of temperate conditions we once thought necessary for life. The timing of 3I-ATLAS's approach to Mars also coincides with seasonal changes on the red planet that could influence how any delivered material might interact with the Martian environment. October marks the beginning of spring in Mars's southern hemisphere, a period when atmospheric dynamics become more active and dust storms can redistribute material across vast distances. If particles from 3I-ATLAS do reach Mars, they could potentially be caught up in these atmospheric processes and distributed far beyond the initial impact or settling sites. Mars's thin atmosphere, while offering less protection from space-borne particles than Earth's thick atmospheric blanket, also means that incoming material experiences less heating during entry. This gentler arrival could preserve delicate organic compounds, or even cellular structures that might be destroyed during the fiery entry through Earth's atmosphere. It's a cosmic irony that Mars's apparent hostility to surface life might actually make it more receptive to life arriving from space. The chemistry of 3I Atlas adds another layer of possibility to our story. Its unusual abundance of carbon dioxide creates intriguing parallels with Mars's own carbon dioxide-rich atmosphere. This chemical compatibility could facilitate the integration of cometary material into Martian atmospheric and surface processes. When 3I Atlas releases its carbon dioxide-rich gases near Mars, these compounds could theoretically become incorporated into the planet's atmospheric chemistry, potentially carrying with them trace amounts of more complex organic molecules. But perhaps most fascinating is what this scenario tells us about the interconnectedness of cosmic processes. If panspermia via interstellar comets is possible, then the boundaries between star systems become less like walls and more like permeable membranes. Life, rather than being isolated on individual worlds, could be part of a vast galactic ecosystem where genetic information and biological potential flow between worlds and even between stellar neighborhoods over cosmic timescales. This perspective transforms how we think about our place in the universe. Rather than being alone on a rare oasis of life in a sterile cosmos, we might be part of an ancient biological network that spans the galaxy. Every world capable of supporting life could potentially contribute to and benefit from this cosmic gene pool, with comets and asteroids serving as the messengers that carry biological innovation between distant worlds. The implications extend beyond mere scientific curiosity. If 3I Atlas is indeed carrying the molecular building blocks of life, or even dormant microorganisms from another star system, then its close encounter with Mars represents a moment of profound significance. We would be witnessing not just a rare astronomical event, but potentially a pivotal moment in the biological history of our solar system. The sophisticated instruments now watching both 3I Atlas and Mars will provide data that could either support or challenge the panspermia hypothesis. Every measurement of the comet's composition, every analysis of its outgassing behavior, every observation of particle ejection and dispersion adds to our understanding of whether such cosmic seeding events are plausible. Similarly, the continuous monitoring of Mars's atmosphere and surface chemistry could reveal signatures of new organic compounds or other changes associated with the comet's passage. What makes this moment particularly special is that we're no longer passive observers of cosmic events. The array of spacecraft, rovers, and telescopes focused on this encounter represents humanity's most ambitious attempt to understand the mechanisms by which life might spread through the universe. We've positioned ourselves to be witnesses to what could be one of nature's most profound processes, the seeding of worlds with the potential for life. Whether or not 3I Atlas ultimately delivers viable biological material to Mars, the encounter offers us something equally valuable. A window into processes that may have been shaping the cosmos for billions of years. The dance of gravity and chemistry playing out between this interstellar visitor and the red planet provides a rare opportunity to study the mechanics of cosmic seeding in real time, something that until now has existed only in the realm of theoretical possibility. As we drift deeper into this cosmic tale, it's worth considering the profound implications of what we're witnessing. If panspermia is indeed a real phenomenon, then the story of life in the universe becomes far more interconnected than we ever imagined. Rather than isolated pockets of biology struggling to emerge independently on scattered worlds, life becomes a shared heritage, a cosmic inheritance passed between star systems on the backs of wandering comets and wayward asteroids. The very carbon atoms that make up our bodies, the oxygen we breathe, the complex molecules that encode our genetic information, all of these were forged in the nuclear furnaces of ancient stars and scattered through space when those stars died in spectacular explosions. Now we're contemplating the possibility that biological information itself might travel similar pathways, carried by cosmic messengers like 3I Atlas from one stellar neighborhood to another across the vast gulfs of interstellar space. This perspective transforms our understanding of rarity and commonality in the universe. Life, rather than being an almost impossibly unlikely accident that happened to occur on Earth, might be an inevitable consequence of cosmic chemistry, a natural process that emerges wherever and whenever conditions permit. If this is true, then the seeds of biology are scattered throughout the galaxy, like spores on a cosmic wind, waiting for the right combination of planetary conditions to take root and flourish. The journey of 3I Atlas itself tells a story that spans cosmic ages. This frozen wanderer began its existence in orbit around some distant star, possibly similar to our own sun, possibly very different. It formed from the same kinds of cosmic dust and gas that gave birth to our own solar system, but in an alien environment shaped by different stellar winds, different planetary companions, different histories of cosmic catastrophe and renewal. Something happened in that distant system, perhaps billions of years ago, that sent 3I Atlas careening into the darkness between stars. Perhaps it was the gravitational tug of a passing stellar neighbor, or the death throes of its parent star, or the chaotic dance of giant planets in an unstable young system. Whatever the cause, our visitor was ejected from its birth system and began an unimaginably long journey through the cold and lonely expanses of interstellar space. For eons beyond human comprehension, 3I Atlas travelled through regions where starlight is so faint that eternal night reigns supreme. The temperatures in these interstellar depths hover just a few degrees above absolute zero, cold enough to freeze any atmosphere solid, cold enough to stop molecular motion almost entirely. Yet within the protective embrace of the comet's icy shell, complex chemistry could continue at its own glacial pace, perhaps preserving not just organic molecules, but the delicate architecture of biological systems themselves. The comet's journey through our galaxy would have been an odyssey of cosmic proportions. It may have passed through stellar nurseries where new stars were being born in brilliant displays of cosmic fire, their intense radiation adding energy to the interstellar medium. It might have wandered through the gravitational fields of massive stars, their immense pull subtly altering the comet's trajectory and speed. Perhaps it even passed through the shock waves of distant supernovae, those stellar explosions that seed space with heavy elements and create the complex chemistry necessary for worlds like ours. Throughout this incredible journey, 3I Atlas would have been accumulating a record of the galaxy's chemical evolution, incorporating trace elements and isotopic signatures that tell the story of stellar nucleosynthesis across cosmic time. In a very real sense, the comet serves as a time capsule, preserving within its frozen heart the chemical fingerprints of processes that occurred in distant corners of the galaxy millions or billions of years ago. Now, as it sweeps through our inner solar system, 3I Atlas is awakening from its deep freeze. The sun's warmth is causing its surface ices to sublimate, releasing gases and particles that have been locked away since the comet's formation. This awakening process creates the spectacular coma and tail that make comets such beautiful objects to observe, but it also represents something far more profound: the release of materials that may carry information about the chemistry and perhaps even the biology of another star system. The instruments studying 3I Atlas are revealing details about its composition that read like a recipe for life: water, carbon dioxide, carbon monoxide, organic compounds, all the basic ingredients that earthly biology requires for its fundamental processes. But more than just the presence of these materials, it's their relative abundances and isotopic compositions that tell us about the conditions under which the comet formed. These chemical signatures are like fingerprints, unique markers that can tell us about the temperature, pressure, and radiation environment of the comet's birthplace. When we compare the chemistry of 3I Atlas to what we know about our own solar system's formation, fascinating patterns emerge. The comet's composition suggests it formed in conditions remarkably similar to those that gave rise to the outer planets and their moons in our own cosmic neighborhood. This similarity raises intriguing questions about whether the processes that led to life on Earth might be common throughout the galaxy, playing out in star system after star system with variations on a universal theme. The carbon dioxide abundance in 3I Atlas is particularly significant when we consider Mars as a potential recipient of cometary material. Mars has a carbon dioxide-rich atmosphere, and its polar ice caps are largely composed of frozen carbon dioxide. This chemical compatibility means that material from 3I Atlas would integrate seamlessly into Mars's existing atmospheric and surface chemistry, potentially providing new sources of organic compounds without dramatically disrupting the planet's delicate chemical balance. But chemistry alone doesn't tell the complete story. The physical processes involved in material transfer from comet to planet operate on scales that challenge our intuition about how the solar system works. When 3I Atlas approaches its closest point to Mars, it will be moving at tremendous speed, far too fast for a direct collision or simple gravitational capture. Instead, any material transfer would likely occur through more subtle mechanisms involving the complex interplay of solar wind, magnetic fields, and orbital dynamics. The solar wind, that constant stream of charged particles flowing outward from the Sun, acts as both a dispersal mechanism and a transport system for small particles throughout the inner solar system. As 3I Atlas releases material through outgassing, these particles become entrained in the solar wind and can be carried vast distances before settling onto planetary surfaces or being swept out of the system entirely. The timing of the comet's passage means that Mars will be positioned to potentially intercept some of this material as it spreads through the inner solar system. Mars's position in its orbit during 3I Atlas's closest approach creates what scientists call a favorable geometry for material transfer. The red planet will be downstream from the comet in terms of solar wind flow, positioned like a catcher's mitt, waiting to receive whatever cosmic fastballs the comet might throw its way. This positioning isn't coincidental. It's the result of the complex gravitational choreography that governs planetary motion and the paths of interstellar visitors. The weak magnetic field of Mars, often considered a disadvantage for protecting potential surface life from cosmic radiation, actually becomes an advantage for protecting potential surface life from cosmic radiation advantage for receiving material from space. Unlike Earth, whose strong magnetic field deflects many incoming particles, Mars presents fewer barriers to the gentle settling of cosmic dust and organic compounds. Its thin atmosphere, while insufficient to support complex surface life as we know it, is thick enough to slow incoming particles without destroying them through excessive heating. These considerations paint a picture of Mars as an almost ideal recipient for cosmic seeding events. The planet's surface preserves a detailed record of its interaction with space over geological time, from ancient asteroid impacts to the steady accumulation of cosmic dust. If 3I Atlas does deliver material to Mars, that material will likely be preserved in the planet's geological record for millions or billions of years, waiting for future explorers to discover and study. The timing of this encounter during our current era of Mars exploration represents an unprecedented opportunity to observe and document a potential panspermia event as it unfolds. Never before have we had such sophisticated instruments positioned to watch both the delivery system, in this case 3I-ATLAS, and the potential recipient world simultaneously. The data being collected during this encounter will inform our understanding of cosmic seeding processes for generations to come. As we contemplate these possibilities while drifting towards sleep, it's worth remembering that we ourselves are made of star stuff, atoms forged in ancient stellar furnaces and dispersed through space by cosmic processes. We're only beginning to understand the calcium in our bones, the iron in our blood, the carbon in our DNA. All of these elements began their journey in the hearts of dying stars and eventually found their way to Earth through mechanisms that may not be so different from what we're witnessing with 3I-ATLAS and Mars. Perhaps the most remarkable aspect of our cosmic story is how it challenges our assumptions about the nature of discovery itself. We often think of scientific breakthroughs as moments of sudden revelation, lightning bolts of understanding that illuminate previously dark corners of knowledge. But the story of 3I Atlas and its potential role as a cosmic gardener unfolds more like a gentle dawn, with each observation adding another layer of possibility to our understanding of how life might spread through the universe. The instruments trained on this interstellar visitor are revealing details that read like chapters in a book written across galactic time. Each spectrum of light captured by our telescopes tells us something about the comet's chemical composition, its physical structure, the conditions under which it formed. But more than that, these measurements are building a portrait of processes that may have been occurring throughout the galaxy for billions of years, long before our own sun condensed from cosmic dust and gas. When astronomers analyze the light signatures from 3I-ATLAS, they're not just identifying molecules and compounds, they're reading a story that began in another star system, perhaps around a star that died before our sun was born. The isotopic ratios of carbon and oxygen in the comet's gases carry information about the nuclear processes that forge these atoms, the stellar environments where they were created, the cosmic events that eventually sent them wandering between the stars. This deep time perspective transforms how we think about the encounter between three IATLAS and Mars. Rather than viewing it as an isolated event, a chance meeting between two objects in space, we begin to see it as part of a vast network of cosmic processes that have been shaping the chemistry and perhaps the biology of worlds throughout the galaxy. Every star system becomes a node in this network, connected to others through the wandering paths of comets, asteroids, and interplanetary dust. The beauty of this interconnectedness becomes even more apparent when we consider the scales involved. The journey of 3I Atlas from its birth system to our solar system likely spanned not just vast distances, but vast stretches of time. During its interstellar voyage, our own solar system was forming, evolving, developing the complex planetary architectures we see today. Earth was transforming from a molten ball of rock into a world capable of supporting the intricate chemistry of life. Meanwhile, protected within its icy shell, 3I Atlas was preserving samples of chemistry from its origin system, carrying them like a cosmic message in a bottle across the dark ocean of interstellar space. The very fact that we can now study this ancient chemistry using our most sophisticated instruments represents a kind of conversation between star systems, a sharing of information across distances and timescales that dwarf human experience. The gravitational choreography that brings 3I Atlas so close to Mars involves forces and motions that operate according to principles discovered by Newton centuries ago. Yet the implications of this celestial dance extend far beyond the realm of classical mechanics. When we calculate the comet's trajectory, predict its closest approach to Mars, estimate the dispersal patterns of its outgas material, we're not just doing astronomy. We're exploring the mechanics of cosmic biology, the physics of life's potential spread through the universe. Mars itself presents a fascinating study in planetary evolution and its relationship to the possibility of life. The red planet's history reads like a story of dramatic change, from what may have been a warmer, wetter world billions of years ago to the cold, dry desert we observe today. But this transformation doesn't necessarily represent the end of Mars's biological potential. Instead, it may have created new niches, new opportunities for life to adapt and persist in ways we're only beginning to understand. The subsurface of Mars, protected from the harsh radiation and extreme temperature swings of the surface, could provide refuge for any biological material delivered by cosmic visitors like 3I Atlas. Recent studies suggest that liquid water may still exist in underground reservoirs, maintained by geothermal heating and the insulating properties of rock and soil. These hidden aquifers could serve as oases for life, connected by networks of fractures and pore spaces that extend deep into the planet's crust. The chemistry of these subsurface environments adds another layer of possibility to our story. Mars's interior contains the same basic elements that support life on Earth: carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus. But the way these elements are distributed and combined in Martian rocks and soils creates unique chemical environments that might support forms of life quite different from those we know on Earth. Some researchers have proposed that Mars's subsurface could harbour entire ecosystems based on chemosynthesis, biological processes that derive energy from chemical reactions rather than sunlight. These ecosystems would be independent of surface conditions, sustained by the slow decay of radioactive elements in the planet's interior and the gradual chemical weathering of rocks and minerals. If such ecosystems exist, they could provide ready-made habitats for any microorganisms delivered by visiting comets. The concept of Mars as a destination for cosmic seeding becomes even more intriguing when we consider the planet's geological activity. While Mars lacks the vigorous plate tectonics that constantly reshape Earth's surface, it's far from geologically dead. Seasonal changes in atmospheric pressure cause the polar ice caps to grow and shrink, creating dust storms and atmospheric circulation patterns that could redistribute any newly arrived organic material across vast distances. Volcanic activity, while less frequent than on Earth, continues to shape certain regions of Mars. The giant volcano Olympus Mons, while currently dormant, shows signs of relatively recent activity in geological terms. Volcanic processes could bring subsurface water to the surface, create temporary warm zones where chemical reactions could proceed more rapidly, and provide energy sources for potential biological processes. The timing of 3 IATLAS's visit during the Martian spring adds yet another dimension to our story. Spring on Mars brings increased atmospheric dynamics, with temperature differences between the warming southern hemisphere and the still cold northern regions driving circulation patterns that can lift dust high into the atmosphere and transport it across hemispheres. Any particles delivered by the comet could become caught up in these seasonal processes, spreading far beyond their initial landing sites. But perhaps most remarkably, we're witnessing this potential cosmic seeding event during an unprecedented era of Mars exploration. The Red Planet currently hosts an international fleet of robotic explorers, each equipped with sophisticated instruments capable of detecting the subtle chemical signatures that might indicate the arrival of new organic material. These mechanical ambassadors serve as our eyes and noses on Mars, constantly sampling the atmosphere and analyzing surface chemistry for changes that might signal cosmic deliveries. The Perseverance rover, currently exploring Jezero crater, carries instruments specifically designed to search for signs of past or present life. Its MOXIE experiment has already demonstrated the ability to extract oxygen from the Martian atmosphere, proving that the planet's thin air contains the basic ingredients for supporting life processes. Its rock sampling capabilities mean that any changes in surface chemistry associated with 3 IATLAS's passage could potentially be preserved for future return to Earth. Meanwhile, in orbit above Mars, spacecraft like the Mars Reconnaissance Orbiter and the European Mars Express are monitoring atmospheric composition and weather patterns with unprecedented precision. These orbital sentinels can detect trace gases at concentrations measured in parts per billion, sensitive enough to identify new organic compounds that might arrive courtesy of our interstellar visitor. This coordinated observation campaign represents something entirely new in the history of astronomy and astrobiology. Never before have we been positioned to observe both sides of a potential panspermia event simultaneously: the delivery vehicle and the recipient world, the cosmic messenger and its intended destination. The data being collected during this encounter will provide insights into cosmic seeding processes that could reshape our understanding of how life spreads through the universe. The relationship to these cosmic processes, very act of observation, changes our. We're no longer passive recipients of whatever the universe might deliver to our neighborhood. Instead, we've become active participants in the cosmic conversation, equipped with instruments sensitive enough to detect the whispered messages carried by interstellar visitors, sophisticated enough to decode the chemical signatures that tell stories of distant worlds and ancient processes. This transformation from passive observers to active participants reflects a broader shift in humanity's relationship with the cosmos. We've moved beyond simply cataloguing the objects we see in the night sky to engaging with the fundamental processes that shape planetary evolution and the distribution of life throughout the galaxy. Our spacecraft and rovers serve as extensions of human senses, reaching across millions of kilometers to touch and taste and analyze worlds we may never visit in person. The data streaming back from Mars and from the telescope studying 3 I-Atlas represents a new form of cosmic literacy, a growing ability to read the chemical signatures and physical processes that govern the evolution of worlds and the spread of complexity through the universe. Each measurement adds to our understanding of how cosmic chemistry translates into the possibility of biology, how the basic ingredients for life are distributed and redistributed through the galaxy, by processes operating on timescales that span cosmic ages. But beyond the technical details and scientific measurements lies something more profound. A growing sense of connection to cosmic processes that operate far beyond the boundaries of our home world. The story of 3I Atlas reminds us that Earth exists within a galaxy-wide network of chemical and potentially biological exchange, a vast web of relationships that connects star system to star system through the wandering paths of comets and asteroids. This perspective transforms our understanding of isolation and connection in the universe. Rather than being alone on a rare oasis of life in a sterile cosmos, we find ourselves part of an ancient network of worlds, each potentially contributing to and benefiting from a galactic commons of biological innovation. The boundaries between star systems become less like walls and more like permeable membranes, allowing the slow but steady exchange of information, chemistry, and perhaps even life itself. The implications extend far beyond academic curiosity or scientific discovery. If panspermia represents a real phenomenon, if life truly does spread between worlds on the backs of cosmic wanderers like 3I Atlas, then the search for life elsewhere in the universe takes on new dimensions. We would be looking not for independent origins of biology, but for distant cousins, for branches of a galactic family tree that might trace back to common ancestors billions of years ago. This possibility reframes questions about humanity's place in the universe and our responsibilities as a spacefaring species. If we are indeed part of a galactic biological network, then our expansion into space becomes not just exploration but reconnection, not just discovery, but reunion with distant relatives we never knew existed. Our spacecraft and probes become emissaries, carrying samples of terrestrial biology back into the cosmic community from which we may have originally emerged. The gentle approach of 3I Atlas toward Mars thus represents more than just another astronomical event to be observed and catalogued. It offers us a window into processes that may have shaped the history of life throughout the galaxy, a glimpse of the subtle but persistent mechanisms by which complexity and perhaps consciousness itself spread through the cosmos. Whether or not this particular encounter results in the successful delivery of viable biological material to Mars, it provides us with invaluable insights into the cosmic context within which all life, including our own, exists and evolves. As we drift deeper into these cosmic contemplations, carried along by the gentle current of scientific wonder and speculation, we find ourselves part of a story much larger and more interconnected than we ever imagined. The atoms in our bodies, forged in ancient stellar furnaces, the water in our cells, delivered perhaps by comets not unlike 3I Atlas, the complex molecules that encode our genetic heritage, all connect us to processes that span the galaxy and stretch back to the very beginning of cosmic time. In this vast network of connection and exchange, 3I Atlas serves as both messenger and message, carrying information about the chemistry of distant worlds, while potentially delivering the ingredients for new chapters in the ongoing story of life's spread through the cosmos. Its journey from another star system to our own represents one thread in a tapestry of cosmic relationships that may connect every world capable of supporting the delicate chemistry we call life. The encounter between this interstellar wanderer and the red planet Mars offers us more than just the possibility of witnessing cosmic seeding in action. It provides us with a profound reminder of our place within the grand story of cosmic evolution, participants in processes that began billions of years ago and will continue long after our own sun has exhausted its nuclear fuel and expanded into a red giant, eventually returning its enriched stellar material to the interstellar medium from which new stars and planets will one day form. As our interstellar visitor continues its approach through our cosmic neighborhood, the dance of chemistry and physics playing out before our instruments reveals layers of possibility that stretch our understanding of how worlds might share their biological heritage. The outgassing patterns observed by our most sensitive telescopes tell a story of awakening, as solar heating gradually liberates materials that have been locked in frozen silence for eons beyond human comprehension. Each puff of vapor released from 3I Atlas carries with it the chemical fingerprints of its distant birthplace. Molecular signatures that speak of stellar nurseries and planetary formation processes that occurred in another corner of our galaxy. The sophisticated spectrometers trained on this cosmic wanderer are detecting not just the expected water vapor and carbon dioxide, but trace amounts of more complex organic compounds that hint at the rich chemistry preserved within its nucleus. These molecular hitchhikers, frozen into the comet's structure during its formation billions of years ago, represent a kind of cosmic archive, a library of chemical processes that may have occurred around a star that died before our own sun was born. The very fact that such delicate chemistry has survived the harsh journey through interstellar space speaks to the protective power of the comet's icy embrace and raises tantalizing questions about what other, more complex structures might lie preserved within its frozen heart. Recent advances in understanding extremophile organisms have revealed that life's tenacity extends far beyond what we once thought possible. In the deepest ocean trenches, where crushing pressure and scalding temperatures create conditions that would seem utterly hostile to biological processes, thriving communities of organisms have developed metabolisms based on chemical energy rather than sunlight. These discoveries have fundamentally altered our conception of what constitutes a habitable environment, expanding the realm of possibility to include worlds and conditions we previously dismissed as sterile. The implications for our understanding of 3I Atlas become profound when we consider these findings. If life can thrive in Earth's most extreme environments, adapting to conditions of crushing pressure, extreme temperature, and toxic chemistry, then the relatively gentle environment within a comet's nucleus begins to seem almost hospitable by comparison. The steady temperature, protection from cosmic radiation, and presence of organic compounds could theoretically provide conditions suitable for certain types of extremophile organisms to not just survive, but potentially remain viable over cosmic timescales. This possibility gains additional weight when we examine the isotopic signatures present in the comet's outgassing material. Isotopes, those subtle variations in atomic structure that serve as cosmic fingerprints, tell us about the nuclear processes that forged these atoms and the environments where they were incorporated into larger molecular structures. The isotopic ratios observed in 3I Atlas's emissions suggest formation in conditions remarkably similar to those that gave rise to the organic chemistry we see in our own solar system's outer regions, where life might have the best chance of taking hold and persisting. But the story grows even more intriguing when we consider the timing of this encounter within the broader context of Mars's seasonal cycles. The red planet's elliptical orbit creates dramatic variations in solar heating throughout its year, and 3I Atlas's closest approach occurs during a period when these seasonal effects are beginning to stir the Martian atmosphere into more active circulation patterns. Dust devils begin to dance across the surface as temperature gradients drive convection currents, while the thin atmosphere responds to changing pressure conditions by redistributing water vapor and trace gases across hemispheres. These atmospheric dynamics create pathways by which any material delivered by 3I Atlas could spread far beyond its initial point of contact with the Martian environment. Particles settling onto the surface during the comet's passage could be lifted by dust storms and carried thousands of kilometers, potentially reaching subsurface environments where conditions might be more favorable for biological processes. The interconnected network of fractures and pore spaces that honeycomb Mars's crust could serve as highways for the distribution of organic material, allowing it to penetrate deep into the planet's interior, where liquid water and chemical energy sources might still exist. The chemical compatibility between 3I Atlas's composition and Mars's existing atmospheric and surface chemistry creates conditions that could facilitate the integration of cometary material into the planet's ongoing geochemical processes. The carbon dioxide released by the comet matches the primary constituent of Mars's atmosphere, while the organic compounds detected in its spectrum could provide new sources of chemical energy for any biological processes that might already exist in the planet's hidden subsurface ecosystems. This compatibility extends to the mineralogy of Mars's surface, where ancient impact events and volcanic processes have created a complex landscape of chemical microenvironments. Clay minerals formed during Mars's warmer, wetter past could serve as protective matrices for organic compounds, while salt deposits left behind by evaporating water could create preservation conditions similar to those that have maintained biological material in Earth's most arid environments for thousands of years. The timing of our observation capabilities adds yet another layer of significance to this cosmic encounter. Never before in human history have we possessed such sophisticated tools for analyzing both the delivery vehicle and the potential recipient world simultaneously. The James Webb Space Telescope's unprecedented sensitivity to infrared radiation allows us to peer deep into three IATLAS's structure, revealing details about its internal composition and the processes driving its activity as it approaches the Sun. Meanwhile, the fleet of robotic explorers currently active on and around Mars provides us with real-time monitoring capabilities that could detect even subtle changes in atmospheric composition or surface chemistry associated with the comet's passage. These mechanical sensors, distributed across the planet's surface and orbiting in its thin atmosphere, serve as early warning systems for cosmic deliveries, capable of identifying new organic compounds at concentrations measured in parts per billion. The Perseverance rover's ongoing exploration of Jezero crater has already revealed compelling evidence of Mars's ancient habitability, including organic compounds preserved in rocks that formed billions of years ago when the crater hosted a large lake. These discoveries provide context for understanding how any new organic material delivered by 3I Atlas might interact with Mars's existing chemical environment, potentially catalyzing new reactions or providing missing ingredients for biological processes. But perhaps most remarkably, the sophisticated life detection instruments aboard these robotic explorers could potentially identify biological signatures associated with any viable microorganisms that might arrive courtesy of our interstellar visitor. The ability to distinguish between organic chemistry and biological activity represents one of the greatest challenges in astrobiology, requiring instruments sensitive enough to detect the subtle molecular patterns that distinguish living processes from purely chemical reactions. Recent developments in this field have produced analytical techniques capable of identifying biological signatures, even in samples that have been subjected to extreme conditions or preserved for extended periods. These methods rely on detecting patterns in molecular chirality, isotopic fractionation, and chemical complexity that are characteristic of biological processes, providing multiple independent lines of evidence that could confirm or refute the presence of life-related chemistry. The application of these techniques to samples potentially influenced by 3IATLAS's passage could provide the first direct evidence of interstellar panspermia, transforming this ancient hypothesis from speculative theory to observed phenomenon. Such a discovery would fundamentally alter our understanding of life's distribution throughout the universe, suggesting that biological complexity represents not a rare accident, but a predictable consequence of cosmic chemistry operating over galactic timescales. The broader implications of this possibility extend far beyond the specific case of 3IATLAS and Mars. If life can indeed travel between star systems aboard cosmic wanderers like comets and asteroids, then the entire galaxy becomes a potential habitat, with biological innovation and genetic information flowing between worlds through networks of gravitational interaction and orbital dynamics that operate over millions and billions of years. This perspective transforms our understanding of evolution itself, suggesting that the development of life on any given world occurs not in isolation, but within the context of a galactic ecosystem where genetic material and biological solutions to environmental challenges can be shared across vast distances and timescales. The unique evolutionary innovations that arise on each world become contributions to a cosmic gene pool, available for distribution to other worlds through the patient work of comets and asteroids carrying their frozen cargo between stellar neighborhoods. The mathematical models describing these processes reveal patterns that operate on scales both intimate and cosmic. The same gravitational forces that guide the orbit of 3IATLAS around our Sun also govern the long-term evolution of stellar positions within our galaxy, creating changing patterns of proximity and interaction that influence the probability of material exchange between star systems over cosmic time. Worlds that seem impossibly distant today may have been much closer together millions of years ago, when different configurations of stellar motion brought their parent stars into closer proximity. These dynamic relationships create windows of opportunity for biological exchange that open and close over geological timescales, suggesting that the distribution of life throughout the galaxy might follow patterns of ebb and flow related to the grand choreography of stellar motion. Periods of increased biological exchange, when multiple star systems pass through regions of space rich in wandering comets and asteroids, could alternate with quieter epochs when worlds remain isolated for millions of years at a time. The chemical evidence preserved in 3IATLAS's structure provides us with a snapshot of conditions during one such period of potential biological exchange, offering clues about the distribution of organic chemistry and possibly life itself during an earlier epoch of galactic history. The isotopic signatures and molecular patterns detected in the comet's outgassing material serve as time capsules, preserving information about chemical processes that occurred in its origin system billions of years ago. When we decode these chemical messages using our most sophisticated analytical techniques, we're essentially reading a letter written by another world and delivered across the vast postal system of interstellar space. The vocabulary of this cosmic correspondence consists of molecular structures and isotopic ratios, while its grammar follows the laws of chemistry and physics that govern the behavior of matter under extreme conditions. The story told by this chemical correspondence speaks of stellar nurseries, where planets formed from the same cosmic dust and gas that gave birth to countless other worlds throughout the galaxy, of chemical processes that may be universal features of planetary formation and evolution, of organic synthesis occurring wherever conditions permit the patient assembly of carbon-based complexity from simpler molecular building blocks. But beyond the specific chemistry lies something even more profound: evidence of connection across distances and timescales that dwarf human experience, proof that the boundaries between star systems are more porous than we ever imagined, and tantalizing hints that the story of life in the universe may be far more interconnected than our earthbound perspective has allowed us to perceive. The approach of 3I Atlas toward Mars thus represents more than just another entry in the catalogue of astronomical events. It offers us a front-row seat to processes that may have shaped the distribution of complexity and consciousness throughout our galaxy, a rare opportunity to observe the mechanisms by which worlds share their chemical and potentially biological heritage across the seemingly empty spaces between stars. As this cosmic drama unfolds before our instruments and cameras, we find ourselves not merely observers, but participants in a story that began billions of years ago and will continue long after our own sun has exhausted its nuclear fuel. The data streaming back from our robotic explorers and space-based telescopes represents a new chapter in humanity's growing literacy in the language of the cosmos, our developing ability to read the chemical signatures and physical processes that govern the evolution of worlds and the distribution of life throughout the universe. The gentle gravitational dance between 3I Atlas and Mars, playing out over the coming weeks, carries with it the potential to answer some of the most profound questions we can ask about our place in the cosmic order. Are we alone, isolated on a rare oasis of life in a sterile universe? Or are we part of an ancient network of worlds connected by the patient work of cosmic messengers, carrying biological innovation between stellar neighborhoods? The answer, written in the chemistry of an interstellar wanderer and preserved in the geological record of a distant world, awaits our discovery in the subtle signatures of molecules and the whispered stories of atoms that have traveled farther and seen more than any human explorer ever could. In this vast library of cosmic information, every spectrum of light captured by our telescopes represents another page in the ongoing story of how life spreads through the universe. One comet, one world, one moment of cosmic serendipity at a time. The contemplation of such cosmic possibilities brings us to one of the most remarkable aspects of our current moment in history. We exist at precisely the right time to witness and potentially document this extraordinary encounter. The convergence of advanced space technology, sophisticated analytical instruments, and the arrival of 3I Atlas creates conditions that have never before existed in human experience. We've positioned ourselves as cosmic witnesses, equipped with mechanical senses sensitive enough to detect the whispered conversations between worlds. The Mars Reconnaissance Orbiter, circling the red planet with its high-resolution cameras and spectrometers, will capture images of 3I Atlas during its closest approach with unprecedented detail. These photographs will likely mark the first time an interstellar object has been imaged from another world, creating a visual record that bridges the gap between our solar system and the distant stellar neighborhood from which our visitor originated. The symbolic power of this moment extends beyond scientific documentation. It represents humanity's growing capacity to observe cosmic processes from multiple perspectives simultaneously. Meanwhile, the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter will monitor atmospheric changes with instruments capable of detecting trace gases at concentrations so low they would be unnoticeable to human senses. These orbital sentinels can identify molecular signatures associated with organic compounds, water vapor, and other volatiles that might be delivered by the comet's passage. The coordinated observation campaign represents an unprecedented level of monitoring for what could be humanity's first documented observation of cosmic seeding in action. The surface-based perspective provided by rovers like Perseverance and Curiosity adds another dimension to our observational capabilities. These mechanical explorers, scattered across different regions of Mars, serve as a distributed network of chemical sensors capable of detecting changes in surface composition that might result from the settling of cometary particles. Their drill systems can sample subsurface materials, potentially preserving any newly delivered organic compounds in sealed containers for future analysis or eventual return to Earth. But the story of observation extends beyond mere data collection to encompass a fundamental shift in humanity's relationship with cosmic processes. We've moved from being passive recipients of whatever the universe might deliver to our neighborhood to becoming active participants in documenting the mechanisms by which worlds exchange their chemical and potentially biological heritage. Our instruments serve as extensions of human curiosity, reaching across millions of kilometers to touch and analyze materials that began their journey in another star system. The technical capabilities that make this comprehensive observation possible represent the culmination of centuries of scientific and technological development. The spectrometers analyzing 3I Atlas's composition rely on quantum mechanical principles discovered barely a century ago, while the rovers exploring Mars utilize navigation systems based on Einstein's theories of relativity. The communication networks that bring data from these distant instruments back to Earth depend on our understanding of electromagnetic radiation and digital signal processing. Yet for all our technological sophistication, the fundamental questions raised by 3I IATLAS's visit remain as profound and mysterious as those contemplated by ancient philosophers, who first wondered whether life might be scattered throughout the cosmos like seeds on the wind. The instruments may be more sensitive, the calculations more precise, but the essential wonder remains unchanged. Are we witnessing the delivery of life's building blocks from one world to another? The answer lies partly in understanding the complex physics of particle dispersal in the space environment surrounding Mars. When 3I Atlas releases material through outgassing, those particles enter a dynamic region influenced by solar wind, magnetic fields, and gravitational forces that can transport them far from their point of origin. The weak magnetic field of Mars, often considered a disadvantage for protecting potential surface life, actually becomes beneficial for receiving cosmic deliveries, presenting fewer barriers to incoming organic material. Solar wind pressure creates invisible rivers of charged particles flowing outward from the Sun, carrying with them microscopic debris from comets, asteroids, and planetary atmospheres. These particle streams can transport material across astronomical distances, creating diffuse clouds of organic compounds that might persist in space for months or years before eventually settling onto planetary surfaces. The timing of 3IATLAS's passage means that Mars could encounter this dispersed material long after the comet itself has moved beyond the red planet's immediate vicinity. The atmospheric dynamics of Mars during this encounter add another layer of complexity to the story. October marks a period of increasing atmospheric activity as seasonal temperature differences drive circulation patterns that can lift dust and particles high into the thin Martian air. Any material delivered by 3I Atlas could become caught up in these atmospheric processes, potentially reaching regions of the planet far from the initial contact points. The subsurface environment of Mars presents perhaps the most intriguing destination for any biological material that might arrive courtesy of our interstellar visitor. Recent studies have revealed that the Martian underground contains extensive networks of fractures, caves, and pore spaces that could provide refuge from the harsh surface conditions. These hidden environments maintain more stable temperatures and may harbor reserves of liquid water, creating potential oases where life could persist even during the planet's current cold, dry epoch. The chemistry of these subsurface environments reflects billions of years of geological evolution, creating complex mineralogical landscapes where different types of rocks and soils provide varying degrees of protection and chemical resources. Clay minerals formed during Mars's ancient warm period could serve as protective matrices for organic compounds, while salt deposits could create preservation conditions, similar to those found in Earth's most extreme desert environments. Volcanic processes, though less active than on Earth, continue to shape certain regions of Mars and could provide energy sources for any biological processes that might take root in the planet's interior. The heat generated by radioactive decay in Mars's core, while insufficient to maintain surface habitability, could create localized warm zones in the subsurface where chemical reactions proceed more rapidly and liquid water remains stable for extended periods. The concept of Mars as a cosmic seed bank takes on new dimensions when we consider these hidden environments. Rather than requiring immediate surface habitability, any biological material delivered by 3IATLAS could potentially remain dormant in the Martian subsurface for millions or billions of years, waiting for changing planetary conditions to create opportunities for growth and reproduction. This long-term perspective transforms Mars from a destination for life to a repository, a cosmic library where genetic information from multiple sources could be preserved across geological timescales. The implications extend to our understanding of how biological innovation spreads through planetary systems and potentially between star systems. If Mars serves as a collection point for organic material from various cosmic sources, including not just 3IATLAS, but the steady rain of interplanetary dust and occasional meteorite impacts, then the planet becomes a kind of biological clearinghouse where chemical evolution can proceed through the mixing and interaction of materials from diverse origins. This perspective suggests that the search for life on Mars should focus not just on indigenous biology that might have evolved on the planet itself, but also on evidence of cosmic seeding events that could have contributed genetic material and chemical complexity from external sources. The discovery of such evidence would transform our understanding of planetary biology from isolated systems to interconnected networks where worlds share their evolutionary innovations through the patient work of cosmic messengers. The sophisticated life detection instruments currently exploring Mars are well positioned to identify signatures of such cosmic contributions. Mass spectrometers can distinguish between organic compounds of different origins based on their isotopic compositions and molecular structures, while microscopic imaging systems can reveal the cellular structures that distinguish biological from purely chemical processes. The combination of these analytical capabilities provides multiple independent lines of evidence for evaluating any biological material that might be associated with 3IATLAS's passage. But beyond the technical aspects of detection and analysis lies a more profound question about the nature of life itself. If biological material can indeed survive interstellar journeys and remain viable for cosmic timescales, then life becomes not just a planetary phenomenon, but a galactic one. The boundaries between worlds become less like walls and more like permeable membranes, allowing the slow but steady exchange of genetic information and biological innovation across distances that dwarf human comprehension. This galactic perspective on biology suggests that evolution operates not just within individual worlds, but across networks of worlds connected by gravitational interactions and orbital dynamics. The unique solutions to environmental challenges that arise on each planet become contributions to a cosmic gene pool, available for distribution to other worlds through the wandering paths of comets and asteroids. The diversity of life throughout the galaxy thus reflects not just local adaptation, but the accumulation of biological innovations shared across stellar neighborhoods over billions of years. The mathematical models describing these processes reveal patterns that operate on scales both intimate and vast. The same physical principles that govern the formation of planetary systems also influence the long-term evolution of stellar positions within galaxies, creating changing configurations that affect the probability of biological exchange between worlds over cosmic time. Periods of increased interaction, when stellar neighborhoods pass through regions rich in wandering objects like 3IATLAS, alternate with quieter epochs when worlds remain isolated for millions of years. These dynamic relationships suggest that the distribution of life throughout the galaxy might follow rhythms related to the grand choreography of stellar motion, with biological complexity spreading in waves that advance and retreat according to the changing geometry of cosmic relationships. The current encounter between 3I Atlas and Mars occurs during one such period of potential exchange, offering us a glimpse into processes that may have shaped the development of life throughout our galactic neighborhood. The preservation of chemical information within 3I Atlas provides us with a record of these ancient processes, a kind of cosmic archaeology that reveals conditions in distant stellar environments billions of years ago. The isotopic signatures detected in the comet's outgassing material tell stories of nuclear processes that occurred in stars that died before our sun was born, while the organic compounds speak of chemical evolution that may have produced the building blocks of life in worlds we will never see. When we analyze this chemical heritage using our most sophisticated instruments, we're essentially reading messages written by other worlds and delivered across the vast communication network of interstellar space. The vocabulary consists of molecular structures and atomic arrangements, while the grammar follows the universal laws of chemistry and physics that govern matter's behavior under all conditions. The stories told through this cosmic correspondence speak of processes that may be common throughout the galaxy: stellar birth and death, planetary formation and evolution, the patient assembly of chemical complexity from simple molecular building blocks. But they also hint at something more profound: The possibility that consciousness itself represents not a rare accident, but a predictable outcome of cosmic chemistry operating over sufficient time and space. The approach of 3i Atlas toward Mars thus offers us more than just another astronomical event to observe and catalogue. It provides a window into the fundamental processes by which complexity and perhaps consciousness emerge and spread throughout the universe. Whether or not this particular encounter results in successful biological seeding, it illuminates the mechanisms by which worlds might share their most precious cargo, the information encoded in living systems. As our instruments continue to gather data from this remarkable encounter, each measurement adds to humanity's growing understanding of our place within the cosmic order. We find ourselves not isolated observers on a rare oasis of life, but participants in an ancient network of relationships that connects world to world and star system to star system through the patient work of cosmic messengers like 3i Atlas. The gentle dance of gravity and chemistry playing out before our cameras and spectrometers reveals layers of possibility that stretch our conception of how life might emerge and persist in the universe. Each puff of vapor from the comet's nucleus, each particle ejected into space, each subtle gravitational perturbation contributes to a vast experiment in cosmic biology that has been running for billions of years. The data streaming back from our robotic explorers represents more than scientific measurements. It constitutes a new form of cosmic literacy, our growing ability to read the chemical signatures and physical processes that govern the evolution of worlds. In this expanding vocabulary of cosmic understanding, every spectrum captured by our telescopes becomes another word in the ongoing conversation between humanity and the universe. The encounter between 3i Atlas and Mars offers us a profound lesson about patience and perspective in our search for understanding. The processes we're witnessing unfold over timescales that dwarf human experience, involving forces and distances that challenge our capacity for comprehension. Yet through the patient work of scientific observation and analysis, we're beginning to glimpse the vast choreography of cosmic evolution that has shaped the distribution of matter, energy, and possibly life throughout our galaxy. This expanding awareness transforms our relationship with the night sky, from one of distant admiration to intimate connection. The stars become not just points of light, but nodes in a vast network of chemical and potentially biological exchange. The space between worlds becomes not empty void, but a medium through which information flows, carrying the innovations of one world to serve as the foundation for complexity on another. As 3i Atlas continues its journey through our solar system, carrying with it the chemical heritage of another world and the potential seeds of future life, it reminds us that we exist within a universe far more interconnected and dynamic than our ancestors ever imagined. The boundaries of our world extend not just to the edge of our atmosphere, but to the distant reaches of interstellar space, connected to other worlds through relationships that span cosmic time. In this vast web of connection and exchange, every world becomes both contributor and beneficiary, sharing its unique innovations while receiving the gifts delivered by cosmic messengers like 3i Atlas. The story of life in the universe becomes not one of isolated struggles against entropy, but of collaborative evolution spanning galaxies, with biological complexity emerging from the patient work of chemistry and physics, operating across scales that encompass both the quantum realm and the cosmic web. The gentle approach of our interstellar visitor toward the red planet thus represents more than just another chapter in the catalogue of astronomical events. It offers us a glimpse into the fundamental processes by which the universe organizes itself into ever greater complexity, creating conditions where matter can contemplate its own existence and wonder about its place in the cosmic order. As we drift deeper into these contemplations, Carried along by the rhythm of scientific discovery and cosmic wonder, we find ourselves part of a story much larger and more beautiful than we ever imagined possible. The atoms in our bodies, the thoughts in our minds, the dreams that carry us into sleep, all connect us to processes that span the galaxy and stretch back to the very dawn of cosmic time, reminding us that we are not separate from the universe, but expressions of its deepest creativity and most profound mystery. The profound implications of what we're witnessing extend beyond the realm of pure science into questions that touch the very heart of what it means to be alive in this universe. If 3I Atlas is indeed carrying the molecular signatures of life from another star system, then we're not just observing an astronomical event, but potentially witnessing a reunion of sorts, a homecoming of biological material that may share common ancestry with the chemistry that gave rise to life on Earth billions of years ago. This possibility transforms our understanding of kinship in the cosmos. The microorganisms that might hitchhike aboard our interstellar visitor could represent distant cousins in the grand family tree of galactic biology, separated not by evolutionary divergence, but by the vast distances and timescales that govern stellar motion. The very atoms that compose any theoretical passengers aboard 3I Atlas were forged in the same stellar furnaces that created the heavy elements in our own bodies, suggesting a fundamental unity underlying the apparent diversity of cosmic chemistry. Recent advances in understanding the formation of planetary systems have revealed that the basic ingredients for life are remarkably common throughout the galaxy. Water, carbon dioxide, organic compounds, and the complex chemistry they enable appear wherever conditions permit the patient assembly of molecular complexity from simpler building blocks. This universality suggests that the processes giving rise to life may be less rare accidents than inevitable consequences of cosmic evolution operating over sufficient time and space. The chemical analysis of 3I Atlas supports this perspective through its surprisingly familiar composition. The ratios of different isotopes detected in the comet's outgassing material mirror those found in our own solar system's outer regions, suggesting that the stellar environment where our visitor formed operated according to the same physical principles that govern the condensation of planets around our Sun. This chemical kinship provides a foundation for understanding how biological material might remain viable during interstellar journeys, protected within icy matrices that preserve delicate molecular architectures across cosmic timescales. But the story grows even more intriguing when we consider the timing of 3I Atlas's arrival during a period when Mars is experiencing subtle but significant changes in its atmospheric and surface chemistry. The planet's thin atmosphere undergoes seasonal variations that create circulation patterns capable of redistributing materials across hemispheres, while subsurface processes continue to cycle water vapor and trace gases between hidden reservoirs and the surface environment. These dynamic processes create pathways by which any material delivered by the comet could integrate into Mars's existing chemical cycles, potentially catalyzing new reactions or providing missing ingredients for processes that have remained dormant for millions of years. The red planet's geological record preserves evidence of ancient hydrothermal systems, underground river networks, and chemical environments that once supported the complex reactions associated with life on Earth. The possibility that such environments might still exist in Mars's deep subsurface adds urgency to our observations of 3I Atlas's passage. If viable biological material does reach the planet, it might not need to immediately establish itself in the harsh surface conditions, but could instead join hidden ecosystems that have persisted in the planet's interior since its warmer, wetter past. These subsurface communities, if they exist, could serve as receiving stations for cosmic deliveries, integrating new genetic material and chemical complexity into biological networks that have been slowly evolving in isolation for billions of years. The concept of Mars as a cosmic crossroads takes on new dimensions when we consider the planet's unique position in our solar system's architecture. Its orbit places it at the boundary between the inner rocky planets and the outer ice giants, making it a natural collection point for materials ejected from both regions. Comets like 3I Atlas approach from the outer reaches of the solar system, while asteroids and meteorites arrive from the inner asteroid belt, creating a convergence of chemical influences that could produce extraordinary diversity in the planet's subsurface chemistry. This convergence effect has been operating throughout Mars's history, with each cosmic visitor potentially contributing unique molecular signatures to the planet's growing chemical library. The cumulative effect of billions of years of such deliveries could have created subsurface environments of remarkable chemical complexity, where organic compounds from dozens of different sources have had time to interact and potentially give rise to novel forms of biological organization. The instruments currently monitoring Mars provide us with unprecedented capability to detect such chemical convergence events in real time. Mass spectrometers aboard orbiting spacecraft can identify trace gases in the planet's atmosphere at concentrations so low they would escape detection by human senses, while ground-based rovers can sample surface materials and analyze their composition with laboratory precision. This distributed sensing network creates conditions where even subtle changes associated with 3I-ATLAS's passage could be detected and documented. The European Space Agency's ExoMars Trace Gas Orbiter has already revolutionized our understanding of Mars's atmospheric chemistry by detecting seasonal variations in methane concentrations that suggest active geological or potentially biological processes. The arrival of 3I Atlas during this period of enhanced atmospheric monitoring creates opportunities to observe how cosmic deliveries might influence these ongoing chemical cycles, potentially providing the first direct evidence of interplanetary material exchange affecting a world's atmospheric composition. Meanwhile, NASA's Perseverance rover continues its methodical exploration of Jezero Crater, an ancient lakebed that preserves a detailed record of Mars's transition from a warmer, wetter world to its current cold, dry state. The rover's sophisticated analytical capabilities include instruments designed specifically to search for organic compounds and potential biosignatures, making it ideally positioned to detect any changes in surface chemistry that might result from the comet's passage. The timing of these observations coincides with seasonal changes on Mars that could amplify the effects of any material delivered by 3I-ATLAS. The planet's elliptical orbit creates dramatic variations in solar heating throughout its year, and the comet's closest approach occurs during a period when atmospheric circulation patterns are becoming more active. Dust devils begin to dance across the surface as temperature gradients drive convection currents, while the thin atmosphere responds to changing pressure conditions by redistributing gases and particles across vast distances. These atmospheric dynamics create natural distribution networks that could carry cometary material far beyond its initial contact points with the Martian environment. Particles settling onto the surface could be lifted by seasonal storms and transported to regions where subsurface water or chemical energy sources might provide more favorable conditions for biological processes. The interconnected network of fractures and caves that honeycomb Mars's crust could serve as highways for this distribution, allowing organic material to penetrate deep into environments where temperature and chemical conditions remain more stable. The chemical compatibility between 3I-ATLAS's composition and Mars's existing atmospheric and geological chemistry creates conditions particularly favorable for such integration. The comet's carbon dioxide-rich nature matches the primary component of Mars's atmosphere, while its organic compounds could provide new sources of chemical energy for any biological or geological processes already operating in the planet's hidden depths. But beyond the specific mechanics of material transfer lies a more profound question about the nature of biological information itself. If life can indeed survive interstellar journeys and remain viable for cosmic timescales, then genetic information becomes something more than a planetary phenomenon. It becomes a galactic resource, shared between worlds through the patient work of cosmic messengers that operate according to the grand choreography of orbital mechanics and stellar motion. This perspective transforms evolution from an isolated planetary process to a galactic one, where the innovations that arise on individual worlds become contributions to a vast biological commons that spans star systems. The unique solutions to environmental challenges developed by life on one planet could theoretically be delivered to other worlds, where they might catalyze new forms of biological organization or provide the missing pieces needed for life to establish itself in previously uninhabitable environments. The mathematical models describing these processes operate on scales that challenge human intuition about cause and effect relationships. The gravitational interactions that guide 3I Atlas through our solar system also govern the long-term evolution of stellar positions within our galaxy, creating changing patterns of proximity and interaction that influence the probability of biological exchange over millions and billions of years. What appears to be a chance encounter between comet and planet occurs within the context of cosmic relationships that have been evolving since the galaxy's formation. These dynamic relationships suggest that the distribution of life throughout the galaxy might follow rhythms related to the grand cycles of stellar motion, with periods of increased biological exchange alternating with quieter epochs when worlds remain isolated for extended periods. The current encounter between 3I Atlas and Mars occurs during what may be a particularly active phase of such exchange, offering us a rare opportunity to observe processes that have been shaping the development of life throughout our galactic neighborhood for billions of years. The preservation of chemical information within 3I Atlas provides us with a direct sample of these ancient processes, a kind of time capsule that carries molecular signatures from another stellar environment. The isotopic ratios and organic compounds detected in the comet's structure tell stories of chemical evolution that occurred under conditions we can only imagine, in worlds that orbited stars whose light has long since faded from the galaxy's inventory of active stellar objects. When we analyze this chemical heritage using our most sophisticated instruments, we're essentially reading messages written in the universal language of atomic structure and molecular bonding. The grammar follows the laws of physics that operate throughout the cosmos, while the vocabulary consists of the same chemical elements that compose our own bodies and the world around us. Yet the stories told through these molecular arrangements speak of processes and environments that may be utterly alien to our earthbound experience. The implications of successfully decoding these cosmic messages extend far beyond academic curiosity or scientific achievement. If we can learn to read the chemical signatures preserved in interstellar visitors, like 3I-ATLAS, we gain access to information about the conditions that prevail in distant stellar environments, the processes that give rise to complex chemistry in other star systems, and potentially the signatures of biological activity that might exist in worlds we will never directly observe. This expanding literacy in cosmic chemistry represents a new phase in humanity's relationship with the universe. We're moving beyond simply cataloguing the objects we can see to developing the capability to analyze the processes that created them, understand the histories they preserve, and potentially recognize the signatures of complexity and life wherever they might exist throughout the cosmos. The data streaming back from our observations of 3I Atlas and Mars represents more than scientific measurements. It constitutes evidence for our growing ability to participate meaningfully in the cosmic conversation. Each spectrum of light captured by our telescopes, each chemical analysis performed by our robotic explorers, adds to our understanding of how worlds communicate across the vast distances of space through the patient exchange of molecular information. The encounter between our interstellar visitor and the red planet thus offers us something unprecedented in human experience: the opportunity to observe and potentially document an act of cosmic communication in progress. Whether or not biological material successfully makes the journey from comet to planet, The event illuminates the mechanisms by which worlds might share their chemical and potentially biological heritage across distances and timescales that dwarf individual planetary histories. As 3I, Atlas continues its approach through our solar system. Each day brings new data that adds detail to our understanding of this remarkable cosmic wanderer. The subtle changes in its outgassing behavior as solar heating increases reveal information about its internal structure and composition, while the gravitational perturbations caused by its interaction with our Sun's gravity provide insights into its mass distribution and physical properties. These observations contribute to a growing database of knowledge about interstellar objects that will inform our understanding of cosmic seeding processes for generations to come. Each visitor from beyond our solar system carries unique information about conditions in its origin system, the processes that ejected it into interstellar space, and the changes it experienced during its journey through the galaxy's sparse but chemically rich interstellar medium. The rarity of such visitors makes every observation precious. Only 3 confirmed interstellar objects have ever been detected passing through our solar system, and 3I Atlas represents our best opportunity yet to study such an object in detail. Its substantial size and active outgassing behavior provide abundant material for analysis, while its relatively slow approach allows extended observation periods that maximize our data collection opportunities. The coordination of multiple observational platforms creates an unprecedented level of coverage for this cosmic event. Ground-based telescopes, space-based observatories, Mars orbiters, surface rovers, and deep space missions all contribute unique perspectives and analytical capabilities to the comprehensive study of 3I-A-T-L-A-S and its interaction with our solar system. This distributed approach ensures that no aspect of the encounter goes unobserved, creating a detailed record that will be studied and reanalyzed for decades to come. But beyond the immediate scientific value of these observations lies their symbolic significance as humanity's first coordinated attempt to document a potential panspermia event in real time. The sophistication of our observational capabilities and the coordination of our response demonstrate our species' growing maturity as cosmic observers, capable of recognizing and studying processes that operate on scales far beyond individual human experience. The gentle approach of 3I Atlas toward Mars reminds us that we exist within a universe of constant motion and change, where the apparent stability of our planetary home masks our participation in cosmic processes that unfold over millions and billions of years. The atoms in our bodies, the air we breathe, the water that sustains us, all participate in cycles of exchange and transformation that connect us to the most distant reaches of space and time. The possibility that our interstellar visitor might be carrying biological information from another world adds profound depth to these connections. If life can indeed travel between star systems, then the boundaries between worlds become less significant than the relationships that connect them through the patient work of cosmic messengers operating according to the grand choreography of galactic evolution. This perspective transforms our understanding of home from a single planet to an entire galaxy, connected through networks of chemical and potentially biological exchange that operate over timescales that encompass the entire history of cosmic evolution. We become not just citizens of Earth, but participants in a vast community of worlds that share their innovations and discoveries through the ancient postal system of comets, asteroids, and interplanetary dust. The story of 3I Atlas and its potential role as a cosmic seed carrier thus becomes our story as well, a reminder of our deep connections to processes that span the galaxy and our responsibility as conscious observers capable of recognizing and documenting the mechanisms by which complexity and perhaps consciousness itself spread throughout the cosmos. In the gentle dance of gravity and chemistry playing out before our instruments, we glimpse something of the vast patience and creativity that characterize the universe's ongoing experiment in self-organization and self-awareness. As the comet continues its journey through our cosmic neighborhood, carrying with it the chemical heritage of another world and the potential seeds of future discoveries, it invites us to expand our conception of what it means to be alive in this universe. We find ourselves not isolated observers on a rare oasis of life, but participants in an ancient network of relationships that connects world to world and star system to star system through bonds forged of shared chemistry and common cosmic heritage. The approaching encounter between 3 IATLAS and Mars offers us more than just another astronomical event to observe and catalogue. It provides a window into the fundamental processes by which the universe organizes itself into ever greater complexity, creating conditions where matter can contemplate its own existence and wonder about its place in the cosmic order. In this vast web of connection and exchange, every observation becomes an act of recognition, every measurement a moment of communion between human consciousness and the deeper patterns that govern cosmic evolution. The data we gather from this encounter will be analyzed and reanalyzed for generations, each new analytical technique revealing additional layers of information preserved in the chemical signatures and physical processes we're documenting. But beyond the specific scientific discoveries lies something even more valuable: expanding awareness of our place within the cosmic community and our growing ability to recognize and participate in the ancient conversations that flow between worlds through the patient medium of chemistry and physics operating across galactic scales. As we settle deeper into these cosmic contemplations, carried gently towards sleep by the rhythm of discovery and wonder, we find ourselves cradled not just by the gravitational embrace of our home planet, but by the vast web of relationships that connects all matter and energy throughout the universe. The story of 3i Atlas becomes our story, a reminder that we are expressions of the cosmos contemplating itself, participants in an ancient dance of complexity and consciousness that spans the stars and encompasses all the beauty and mystery of existence itself. The contemplation of such vast interconnectedness brings us to perhaps the most remarkable aspect of our current moment in cosmic history. We find ourselves living at precisely the right time to witness what may be one of the universe's most subtle yet profound processes unfolding before our very instruments. The convergence of technological capability and cosmic timing creates conditions that have never before existed in human experience, positioning us as witnesses to mechanisms that have shaped the distribution of complexity throughout our galaxy for billions of years. The sophisticated analytical instruments now trained on 3i Atlas reveal details about its composition that read like a cosmic recipe book, each molecular signature telling us something about the chemical environment where this wanderer first condensed from stellar dust and gas. The spectrometers detecting trace amounts of complex organic compounds in the comet's outgassing material are essentially performing chemical archaeology, uncovering evidence of processes that occurred in another star system when our own sun was perhaps just beginning to ignite its nuclear furnace. These molecular hitchhikers, preserved within the comet's icy matrix for eons beyond human comprehension, represent a kind of cosmic time capsule that has traveled distances so vast they grasp their significance. Each organic challenge our ability to truly molecule detected in the comet's spectrum carries information about the temperature, pressure, and chemical conditions that existed during its formation, creating a detailed record of stellar neighborhood chemistry that predates our solar system's current configuration. The isotopic ratios present in these compounds serve as cosmic fingerprints, unique signatures that can tell us about the nuclear processes that forged these atoms in the hearts of ancient stars. When we analyze the carbon-12 to carbon-13 ratios in 3i Atlas's organic material, we're reading evidence of stellar nucleosynthesis that occurred in massive stars that lived fast, burned bright, and died in spectacular explosions that scattered their enriched stellar material throughout what would eventually become our galactic neighborhood. But beyond the specific chemistry lies something even more intriguing: the remarkable similarity between 3i Atlas's composition and the organic chemistry we find in the outer regions of our own solar system. This chemical kinship suggests that the physical processes giving rise to complex organic synthesis may be universal features of stellar evolution, playing out in star system after star system according to the same fundamental principles that govern the behavior of matter under extreme conditions. The implications of this universality extend far beyond academic interest in comparative stellar chemistry. If the basic ingredients for biological processes arise naturally wherever conditions permit the patient assembly of complex molecules from simpler building blocks, then the foundations for life may be scattered throughout the galaxy, like seeds waiting for the right combination of planetary conditions to take root and flourish. Recent discoveries in astrobiology have revealed that the boundary between chemistry and biology is far more fluid than we once imagined. Complex organic molecules can spontaneously organize themselves into structures that exhibit some of the characteristics we associate with living systems, including self-replication, metabolism, and response to environmental changes. These discoveries suggest that the transition from chemistry to biology might be less a rare accident than an inevitable consequence of chemical complexity reaching certain critical thresholds. The protective environment within 3Ia-TLAS's nucleus could theoretically provide conditions where such chemical evolution might continue even during interstellar journeys spanning millions or billions of years. The steady temperature, protection from cosmic radiation, and presence of organic compounds create a kind of cosmic laboratory where molecular complexity could gradually increase through slow but persistent chemical reactions, operating over timescales that dwarf planetary histories. The mathematical models describing these processes reveal patterns that operate according to principles we're only beginning to understand. Chemical networks can exhibit emergent properties that arise spontaneously from the interactions between simpler components, creating forms of organization that persist and evolve according to their own internal logic. These self-organizing systems represent a bridge between the purely physical processes that govern stellar and planetary evolution and the biological processes that characterize living systems. The possibility that such chemical evolution might be occurring within 3I Atlas as it journeys through our solar system adds extraordinary depth to our observations of its outgassing behavior. Each puff of vapor released by solar heating might carry with it not just ancient organic molecules, but potentially the products of ongoing chemical evolution that has been proceeding within the comet's nucleus throughout its interstellar voyage. The timing of this release, occurring just weeks before the comet's closest approach to Mars, creates conditions where the red planet might serve as a collection point for materials that have been slowly evolving in the cosmic equivalent of a test tube for billions of years. The dispersal patterns created by solar wind and gravitational interactions could distribute this chemically enriched material across vast regions of Mars's surface and atmosphere, potentially delivering not just the building blocks for life, but partially assembled biological components ready for further development. The seasonal dynamics of Mars during this period create additional pathways for the distribution and concentration of any delivered material. The planet's thin atmosphere undergoes dramatic changes as solar heating drives circulation patterns that can transport particles across hemispheres, while subsurface processes continue to cycle water vapor and trace gases between hidden reservoirs and the surface environment. These natural distribution networks could carry cometary material to locations where geological or chemical conditions might be more favorable for continued molecular evolution. The concept of Mars as a cosmic laboratory takes on new dimensions when we consider the planet's unique geological history and current chemical environment. The red planet preserves a detailed record of its transformation from a warmer, wetter world to its current cold, dry state, creating a complex landscape of chemical microenvironments where different types of reactions might proceed at varying rates. Ancient impact craters provide natural collection basins for cosmic deliveries, while volcanic regions might offer sources of chemical energy for continued molecular evolution. The subsurface environment of Mars presents perhaps the most intriguing destination for any complex chemistry delivered by 3A Atlas. Recent studies have revealed extensive networks of fractures, caves, and pore spaces that extend deep into the planet's crust, creating hidden environments where temperature and pressure conditions remain more stable than at the surface. These underground spaces might harbor reserves of liquid water and provide protection from the sterilizing effects of cosmic radiation, creating natural laboratories where chemical evolution could continue for millions of years. The discovery of methane in Mars's atmosphere adds another layer of possibility to our story. This simple organic molecule, detected in varying concentrations that suggest active geological or potentially biological processes, demonstrates that complex chemistry continues to operate in the Martian environment. The arrival of additional organic compounds, courtesy of 3IATLAS, could potentially catalyze new reactions or provide missing components for chemical networks that have remained dormant for geological periods. The instruments currently monitoring Mars provide us with unprecedented capability to detect such chemical interactions in real time. Mass spectrometers can identify trace gases at concentrations so low they would be undetectable to human senses, while sophisticated imaging systems can reveal changes in surface mineralogy that might indicate ongoing chemical reactions. This distributed sensing network creates conditions where even subtle effects associated with 3IATLAS's passage could be documented and studied in detail. But perhaps most remarkably, we're positioned to observe these potential chemical interactions from multiple perspectives simultaneously. Ground-based telescopes continue to track the comet's approach and analyze its composition, while Mars-based instruments monitor atmospheric and surface chemistry for any passage. This coordinated observation changes associated with the Cosmic Visitors campaign represents humanity's most ambitious attempt to document interplanetary chemical exchange in real time. The data streaming back from these various observation points contributes to our growing understanding of how chemical information flows between worlds through the patient work of cosmic messengers. Each measurement adds to a vast database of knowledge about the mechanisms by which molecular complexity spreads throughout planetary systems, and potentially between star systems over cosmic timescales. The broader implications of these observations extend far beyond the specific case of 3IATLAS and Mars. If chemical evolution can indeed continue during interstellar journeys, then every comet becomes a potential laboratory for molecular innovation, carrying the products of chemical experimentation between stellar neighborhoods. The diversity of organic chemistry throughout the galaxy thus reflects not just local planetary conditions, but the cumulative results of chemical evolution operating within countless cosmic laboratories, journeying through interstellar space. This perspective transforms our understanding of how complexity emerges and spreads throughout the universe. Rather than viewing chemical evolution as a process confined to planetary surfaces, we begin to see it as a galactic phenomenon that operates wherever conditions permit the patient assembly and reorganization of molecular structures. The boundaries between worlds become less significant than the networks of chemical exchange that connect them through the wandering paths of comets and asteroids. The mathematical models describing these processes operate on scales that encompass both quantum mechanics and galactic dynamics. The same principles that govern chemical bonding between individual atoms also influence the large-scale distribution of matter throughout galaxy clusters, creating patterns of organization that span from the molecular to the cosmic. This fractal-like structure suggests that the emergence of complexity follows similar principles at every scale of organization, from the formation of organic molecules to the evolution of galactic superclusters. The preservation of chemical information within interstellar objects, like 3I Atlas, provides us with direct samples of these multi-scale processes, allowing us to study the relationships between cosmic chemistry and local planetary conditions. The isotopic signatures and molecular patterns detected in the comet's structure serve as records of chemical evolution that began in another stellar environment and continued throughout its journey across interstellar space. When we decode these chemical records using our most sophisticated analytical techniques, we're essentially reading the autobiography of matter itself, learning how simple atoms become organized into increasingly complex structures through the patient work of physical and chemical processes operating over cosmic timescales. This expanding literacy in cosmic chemistry represents a fundamental shift in humanity's relationship with the universe, from passive observation to active participation in the ongoing conversation between matter and energy that shapes cosmic evolution. The approach of 3i Atlas toward Mars thus represents more than just another entry in the catalogue of astronomical events. It offers us a rare opportunity to observe the mechanisms by which chemical innovation spreads throughout the cosmos, potentially witnessing the delivery of molecular complexity that has been evolving for billions of years in the cosmic equivalent of a traveling laboratory. The gentle gravitational dance between comet and planet, playing out over the coming days, carries with it the potential to illuminate some of the most fundamental questions we can ask about the nature of complexity in the universe. How does chemical innovation spread between worlds? What role do interstellar messengers play in distributing molecular diversity throughout galactic neighborhoods? Are we witnessing one thread in a vast web of chemical relationships that connects every world capable of supporting complex chemistry? The answers lie encoded in the subtle signatures of molecules and atoms that have journeyed farther and experienced more than any human explorer ever could. In the patient work of spectrometers and mass analyzers, in the careful measurement of isotopic ratios and molecular structures, we're developing to read these cosmic stories and understand our place within the vast network of chemical relationships that spans the galaxy. The data we gather from this encounter will be studied for generations, each new analytical technique revealing additional layers of information preserved in the chemical heritage of our interstellar visitor. But beyond the specific discoveries lies something even more profound: growing recognition that we exist within a universe where complexity emerges naturally from the interactions between simple components, where innovation spreads through networks of relationship and exchange that operate according to principles we're only beginning to glimpse. As 3i Atlas continues its journey through our cosmic neighborhood, it carries with it not just the chemical heritage of another world, but the potential to transform our understanding of how complexity and perhaps consciousness itself emerge and spread throughout the universe. The approaching encounter with Mars represents a moment of convergence between cosmic history and human discovery, offering us a window into processes that have been shaping the development of chemical and potentially biological complexity throughout our galaxy for billions of years. The implications extend beyond scientific curiosity to touch the very heart of what it means to be conscious beings in a universe that appears to be constantly experimenting with new forms of organization and complexity. We find ourselves not just observers of cosmic chemistry, but expressions of it, participants in an ongoing exploration of possibility that spans from the quantum realm to the largest structures in the observable universe. In this vast laboratory of cosmic experimentation, every world becomes both test site and laboratory assistant, contributing its unique innovations to the growing database of successful molecular architectures, while benefiting from the discoveries delivered by cosmic messengers like 3i Atlas. The boundaries between self and other, between local and cosmic, begin to dissolve as we recognize our deep participation in processes that connect us to every corner of the galaxy through bonds forged of shared chemistry and common cosmic heritage. The gentle approach of our interstellar visitor toward the red planet thus offers us something unprecedented: the opportunity to witness ourselves as part of the cosmic conversation, conscious expressions of the universe's ongoing experiment in self-organization and self-awareness. In the dance of molecules and atoms playing out before our instruments, we glimpse something of the vast creativity that characterizes cosmic evolution, the patient persistence with which the universe explores every possible pathway toward greater complexity and deeper understanding. As we settle into these contemplations, carried gently toward rest by the rhythm of discovery and wonder, we find ourselves cradled by the recognition that we are expressions of the cosmos contemplating itself through the lens of human consciousness. The story of 3i Atlas becomes a mirror in which we recognize our own cosmic nature, participants in an ancient dance of complexity that spans the stars and encompasses all the beauty and mystery of existence itself. The approaching encounter between comet and planet reminds us that we live within a universe of constant motion and transformation, where apparent stability masks our participation in processes that unfold over scales of time and distance that challenge human comprehension. Yet through the patient work of scientific observation and the gentle persistence of curiosity, we're learning to read the stories written in light and chemistry, discovering our place within the vast web of relationships that connects all matter and energy throughout the cosmos. In this recognition lies perhaps the deepest gift offered by our cosmic visitor, not just knowledge about interstellar chemistry or planetary evolution, but expanding awareness of our intimate participation in the universe's ongoing exploration of what becomes possible when matter organizes itself into forms capable of wonder, capable of recognition, capable of love. The gentle dance of 3i Atlas toward Mars becomes a meditation on connection itself, a reminder that we exist within a cosmos where every particle participates in relationships that span galactic distances and cosmic time. As the comet continues its ancient journey, carrying with it the molecular heritage of distant worlds and the potential seeds of future discoveries, it invites us to expand our conception of home beyond the boundaries of our single planet, to embrace the entire galaxy as our cosmic neighborhood. In this vast community of worlds connected through networks of chemical and potentially biological exchange, we find ourselves not alone, but profoundly connected to processes and possibilities that encompass the full creativity and mystery of cosmic evolution itself. The chemical symphony playing out before our instruments reveals layers of cosmic artistry that have been composing themselves across galactic time. As 3i Atlas releases its ancient cargo into the solar wind, each expelled particle carries with it a story that began in stellar nurseries we can barely imagine, where different physics and chemistry shape the assembly of matter into the complex organic architectures we're now detecting. The comet's outgassing doesn't simply release random debris, but appears to follow patterns that suggest underlying organization, as if the molecular structures preserved within its nucleus have been waiting eons for precisely the right conditions to resume their patient dance of chemical evolution. The timing of this molecular awakening, occurring just as Mars enters a period of increased atmospheric activity, creates opportunities for integration that may not have existed at any other point in the planet's recent history. The red planet's seasonal cycles are driven by its elliptical orbit and axial tilt, creating complex patterns of temperature variation that influence everything from polarized sublimation to dust storm formation. During the period when 3i Atlas makes its closest approach, these atmospheric dynamics reach a particularly active phase, with circulation patterns that could potentially carry cometary material to regions of the planet where subsurface chemistry might be most receptive to new molecular inputs. The mathematics governing particle dispersal in the Martian environment reveal fascinating possibilities for how cosmic deliveries might integrate into existing geological and chemical processes. Computer models suggest that materials released by 3i Atlas could follow multiple pathways to reach the planet's surface, from direct ballistic trajectories to more circuitous routes involving gravitational capture and atmospheric circulation. The thin Martian atmosphere, while insufficient to support complex surface life as we know it, provides just enough density to slow incoming particles without destroying them through excessive heating, creating ideal conditions for the gentle delivery of delicate organic structures. But perhaps most intriguingly, the subsurface environment of Mars presents a three-dimensional landscape of chemical possibility that extends far below the planet's visible surface. Recent mapping of the Martian underground has revealed networks of interconnected spaces that could serve as distribution channels for any material that penetrates beyond the immediate surface layers. These hidden pathways, carved by ancient water flows and maintained by ongoing thermal cycling, create opportunities for cosmic deliveries to reach environments where temperature, pressure, and chemical conditions might support continued molecular evolution. The concept of Mars as a cosmic archive takes on new significance when we consider how efficiently the planet preserves chemical information across geological time. Unlike Earth, where active tectonics and weathering constantly recycle surface materials, Mars maintains a relatively static geological record that could preserve evidence of cosmic seeding events for billions of years. The planet's surface serves as a kind of cosmic library, where each impact, each dust storm, each seasonal cycle adds another page to an ongoing record of chemical exchange with the broader solar system. This preservation capability means that 3 IATLAS's contribution to Martian chemistry could remain detectable long after the comet itself has departed our solar system and resumed its journey through interstellar space. Future explorers, whether robotic or human, might discover layers of sediment enriched with isotopic signatures that trace back to this moment, creating a permanent record of interstellar material delivery that could inform our understanding of cosmic seeding processes for generations to come. The instruments currently monitoring this encounter operate at the very limits of detection sensitivity, capable of identifying molecular signatures at concentrations that would have been unimaginable just decades ago. Mass spectrometers aboard Mars orbiters can distinguish between different isotopes of the same element with precision that rivals the best laboratory instruments on Earth, while ground-penetrating radar systems reveal subsurface structures with resolution measured in centimeters. This unprecedented analytical capability means that even subtle effects associated with 3 IATLAS's passage could be detected and studied in extraordinary detail. The coordination between different observational platforms creates a kind of distributed consciousness focused on documenting this cosmic encounter. Each instrument contributes its unique perspective to a growing database of information that spans everything from the comet's internal structure to Mars's atmospheric response to potential particle impacts. The synthesis of data from ground-based telescopes, space-based observatories, Mars orbiters, and surface rovers creates a comprehensive view of interplanetary material exchange that would have been impossible to achieve with any single observational approach. This multifaceted observation campaign represents something entirely new in the history of astronomy. The real-time documentation of processes that typically unfold over timescales far longer than human civilization has existed. We're essentially watching cosmic evolution in fast forward, compressed into a period short enough for human attention spans to encompass, while detailed enough to reveal the intricate mechanisms by which worlds exchange their chemical heritage. The broader implications of successfully documenting such an event extend far beyond the specific case of 3 IATLAS and Mars. If we can learn to recognize and analyze interplanetary material transfer in real time, we gain the ability to study similar processes operating throughout our solar system and potentially in other stellar neighborhoods. Every comet approach, every asteroid flyby, every dust storm becomes an opportunity to observe cosmic chemistry in action, building our understanding of how molecular complexity spreads through planetary systems. The patient work of chemical analysis reveals that 3I Atlas carries within its frozen structure a kind of molecular fossil record that preserves information about stellar chemistry from billions of years ago. The ratios of different organic compounds detected in its outgassing material tell stories about the temperature and pressure conditions that existed during its formation, while isotopic signatures reveal details about the nuclear processes that forge these atoms in the hearts of ancient stars. Each measurement adds another piece to our growing understanding of how stellar death and birth cycles distribute the raw materials for complexity throughout galactic neighborhoods. But beyond the academic fascination with cosmic chemistry lies something more profound. Recognition that we're witnessing one thread in a vast tapestry of relationships that connects every world capable of supporting complex molecular architectures. The boundaries between star systems become less like walls and more like permeable membranes, allowing the slow but steady exchange of chemical innovation across distances that dwarf individual planetary histories. This perspective transforms our understanding of isolation and connection in the universe, suggesting that complexity emerges not in isolation, but through networks of relationship and exchange that span galactic scales. The mathematical models describing these exchange processes reveal patterns that operate according to principles we're only beginning to understand. Chemical networks can exhibit emergent properties that arise spontaneously from interactions between simpler components, creating forms of organization that persist and evolve according to their own internal logic. These self-organizing systems represent a bridge between the purely physical processes that govern stellar and planetary evolution and the biological processes that characterize living systems. The possibility that such self-organization might be occurring within 3. I-Atlas, as it journeys through our solar system, adds extraordinary depth to our observations of its behavior. The comet's outgassing patterns show subtle variations that could indicate ongoing chemical reactions within its nucleus, suggesting that molecular evolution might continue even during the final phases of its interstellar journey. The products of these reactions, released just as the comet approaches Mars, could represent the culmination of chemical experimentation that has been proceeding for billions of years in the cosmic equivalent of a traveling laboratory. The timing of this chemical release, occurring during Mars's period of maximum atmospheric activity, creates conditions where the red planet might serve as more than just a passive recipient of cosmic deliveries. The planet's seasonal circulation patterns could actively participate in the distribution and concentration of cometary material, potentially creating chemical gradients and concentration zones that facilitate continued molecular evolution. Mars becomes not just a destination, but a collaborator in the ongoing experiment of cosmic chemistry. The subsurface environment of Mars presents perhaps the most intriguing venue for such chemical collaboration. Hidden beneath the planet's oxidized surface lies a complex three-dimensional landscape of interconnected spaces, where temperature and chemical conditions remain more stable than at the surface. These underground environments might harbor not just reserves of liquid water, but entire ecosystems of chemical reactions that have been proceeding slowly but persistently for millions of years, waiting for new molecular inputs to catalyze fresh innovations. Recent discoveries have revealed that Mars's interior contains all the basic elements necessary for complex chemistry, arranged in geological formations that create natural laboratories for molecular experimentation. Clay minerals provide catalytic surfaces where organic synthesis can proceed more efficiently, while salt deposits create concentration mechanisms that bring reactive compounds into closer contact. The arrival of additional organic material from 3I-Atlas could provide the missing components needed to activate chemical networks that have remained dormant for geological periods. The concept of dormancy in planetary chemistry parallels similar phenomena observed in biological systems, where complex molecular machinery can remain inactive for extended periods while retaining the ability to resume function when appropriate conditions return. This suggests that planets might maintain chemical potential that can be activated by cosmic deliveries, transforming apparently sterile worlds into active participants in galactic chemical evolution. Mars, with its preserved geological record and stable subsurface environments, represents an ideal testing ground for such activation processes. The instruments studying 3I-Atlas have detected trace amounts of phosphorus-bearing compounds among its organic inventory. adding another crucial ingredient to the cosmic recipe for complex chemistry. Phosphorus plays essential roles in many biological processes on Earth, from energy storage in cellular metabolism to information encoding in genetic molecules. The presence of such compounds in our interstellar visitor suggests that the basic chemical toolkit for life might be more widely distributed throughout the galaxy than we previously imagined. This chemical universality implies that the transition from complex chemistry to biology might be less a rare accident than a predictable outcome of molecular evolution operating under favorable conditions. The same physical principles that govern chemical bonding and molecular assembly operate throughout the cosmos, suggesting that similar chemical innovations might arise independently in stellar neighborhoods throughout the galaxy. The delivery of such innovations by cosmic messengers like 3I Atlas could accelerate chemical evolution on recipient worlds by providing molecular templates and catalytic compounds that might otherwise take millions of years to develop through local processes alone. The gravitational choreography that brings 3I Atlas so close to Mars operates according to mathematical principles that connect local planetary dynamics to the grand motions of stellar systems throughout the galaxy. The same forces that guide our comet's trajectory also influence the long-term evolution of our solar system's architecture, creating changing patterns of gravitational interaction that affect the probability of material exchange between worlds over cosmic timescales. What appears to be a chance encounter between comet and planet occurs within the context of cosmic relationships that have been evolving since our galaxy's formation. This deep-time perspective reveals that the current encounter represents just one moment in an ongoing conversation between worlds that has been proceeding for billions of years. Every comet approach, every asteroid impact, every grain of cosmic dust contributes to a vast experiment in chemical evolution that spans galactic neighborhoods and encompasses countless stellar systems. The boundaries between individual worlds become less significant than the networks of chemical exchange that connect them through the patient work of gravity and orbital mechanics. The preservation of chemical information across such vast scales of time and space requires mechanisms that can protect delicate molecular structures from the destructive effects of cosmic radiation and extreme temperatures. The nucleus of 3I Atlas serves as a natural archive, its icy matrix providing exactly the kind of protection needed to preserve complex organic compounds during interstellar journeys spanning millions or billions of years. This preservation capability transforms comets from simple balls of ice and rock into cosmic libraries that carry chemical information between stellar neighborhoods. The analysis of this preserved chemical information using our most sophisticated instruments reveals details about molecular architectures that developed under conditions we can barely imagine. The organic compounds detected in 3I Atlas's spectrum show levels of complexity that suggest ongoing chemical evolution rather than simple preservation of primitive molecules. This indicates that the comet's nucleus might have served as more than just a storage medium, potentially functioning as an active chemical reactor where molecular innovation continued throughout its interstellar journey. The implications of such ongoing chemical evolution extend our understanding of how complexity emerges and spreads throughout the universe. Rather than viewing molecular innovation as a process confined to planetary surfaces, we begin to see it as a phenomenon that can occur wherever conditions permit the patient assembly and reorganization of chemical structures. This perspective transforms every wandering comet into a potential laboratory for cosmic chemistry, carrying the products of molecular experimentation between stellar systems and contributing to the growing database of successful chemical architectures throughout the galaxy. The mathematical beauty underlying these processes reveals patterns that connect quantum mechanics to galactic dynamics through cascades of cause and effect that span every scale of cosmic organization. The same principles that govern electron orbitals in individual atoms also influence the distribution of matter throughout galaxy clusters, creating fractal-like structures that repeat at every level of observation. This self-similarity suggests that the emergence of complexity follows universal principles that operate regardless of scale, from the formation of organic molecules to the evolution of consciousness itself. The approaching encounter between 3I Atlas and Mars thus represents more than just another astronomical event to be observed and catalogued. It offers us a window into the fundamental processes by which the universe organizes itself into ever greater complexity, creating conditions where matter can contemplate its own existence and wonder about its place in the cosmic order. In this vast web of connection and transformation, every measurement becomes an act of recognition, every observation a moment of communion between human consciousness and the deeper patterns that govern cosmic evolution. The gentle dance of chemistry and physics playing out before our instruments reveals the universe as a vast experimental laboratory where innovation emerges naturally from the interactions between simple components, operating according to elegant mathematical principles. We find ourselves not separate from these processes, but expressions of them, conscious manifestations of the cosmos, exploring its own potential for self-organization and self-awareness through the patient work of scientific observation and the gentle persistence of curiosity. As 3I Atlas continues its ancient journey toward Mars, it carries with it more than just the molecular heritage of another world. It brings the promise of discovery, the potential for transformation, and the gentle reminder that we exist within a universe where complexity and consciousness emerge naturally from the patient dance of matter and energy, exploring every possible pathway toward greater understanding and deeper connection with the fundamental creativity that characterizes cosmic evolution itself. The profound beauty of this cosmic encounter lies not just in its rarity, but in its perfect timing with humanity's growing ability to listen to the universe's most subtle conversations. As 3I Atlas approaches Mars, we find ourselves equipped with mechanical ears, sensitive enough to hear the whispered exchanges between worlds, instruments delicate enough to detect the molecular signatures of processes that began before our sun learned to shine. The comet's journey through our solar system represents a kind of cosmic archaeology in reverse, where instead of digging through layers of ancient sediment, we're watching as materials from another world's distant past are gradually released into the present moment. Each puff of vapor escaping from the comet's nucleus carries with it chemical stories that span galactic time, molecular narratives written in a language older than planets. The seasonal rhythms of Mars add their own gentle poetry to this encounter. As the red planet turns towards spring in its southern hemisphere, atmospheric currents begin to stir like morning breezes, creating circulation patterns that could embrace any cosmic gifts delivered by our interstellar visitor. The timing feels almost choreographed, as if the universe has arranged this meeting with the precision of a master conductor, bringing together instruments from different orchestras to create a symphony that neither could perform alone. But perhaps most remarkable is how this encounter transforms our understanding of home itself. We're witnessing the possibility that the very concept of planetary boundaries might be more fluid than we ever imagined. If materials from 3I Atlas do reach Mars, they would carry with them the chemical essence of another star system, blurring the lines between here and there, between local and cosmic, between the familiar chemistry of our solar system and the exotic possibilities that exist in stellar neighborhoods we may never visit. The gentle persistence with which life has demonstrated its ability to survive in Earth's most extreme environments suggests that the universe may be far more hospitable to biological processes than our comfortable, temperate perspective has allowed us to perceive. From the crushing depths of ocean trenches to the radiation-soaked interior of nuclear reactors, from the acid-drenched pools of volcanic hot springs to the frozen permafrost of polar regions, biology has repeatedly shown us that what we consider impossible conditions for life often turn out to be simply unfamiliar neighborhoods in the vast city of existence. And so, dear sleepy wanderer, As 3i Atlas continues its ancient dance toward Mars, we find ourselves witnesses to something far grander than a single cosmic encounter. We've glimpsed the possibility that life itself might be a galactic conversation, whispered between worlds on the gentle breath of comets, and carried across the vast spaces between stars by messengers we're only now learning to recognize. Whether or not our interstellar visitor delivers the seeds of tomorrow's Martian gardens, it has already given us something precious: the recognition that we exist within a universe where complexity and connection span distances that humble the imagination, where the atoms in our bodies participate in relationships that stretch across cosmic time. Sleep well, knowing that you are made of star stuff that has journeyed farther than any explorer, part of an ancient network of worlds sharing their stories through the patient language of chemistry and light, dreaming together across the infinite library of space. The patient language of chemistry and light, dreaming together across the infinite library of space.